Hello everyone, welcome to our channel Chemistry Entrance Helps. Today our topic is blackbody radiation. Now, to study blackbody radiation, we must know what is a blackbody. So a blackbody is a body which absorbs any radiation that falls on it. And the radiation which is emitted by a blackbody is known as blackbody radiation. It's also called full radiation because a blackbody absorbs all radiation and emits everything. Now we should know what's a perfect blackbody. In our universe, there is no such body which acts as a perfect blackbody. As shown in the picture, we can consider a cavity with highly insulating wall heated to high temperature is considered as a blackbody. For example, an oven, as it has highly insulating wall, will act as blackbody if there is a small opening. So what's there in the cavity that it acts as a blackbody? First, the wall of the cavity absorbs the radiation, and this radiation causes heating to the cavity walls. Then the atoms in the wall of the cavity starts to vibrate. Finally, those atoms re-radiate the energy at new frequency. Now comes Kirchhoff's law of blackbody radiation. Because to know blackbody, we must know some laws of blackbody. So there are two laws by Kirchhoff. The first one is, besides absorbing radiations, a blackbody also radiates perfectly. So it's a perfect radiator. And secondly, radiation by blackbody depends on the temperature of the cavity. It doesn't depend on the material of the cavity. Then Lumar and Pringsheim experiment. Lumar and Pringsheim observed the variation of power radiated versus wavelength at different temperatures as shown in the figure on the right hand side, where the blue line indicates the variation of intensity. All the peak wavelengths are indicated by the red dotted line. You can see in the picture. So they observed that with increase in temperature at a given wavelength, the energy increases. The intensity decreases but never touches the x-axis. You can see the blue line never touches the x-axis. Then thirdly, the energy density per unit wavelength is more at high temperature than at low temperature. That is, you can see the energy density is, in case of high temperature, is more. So fourth, the intensity at first increases with increase in wavelength and then began to decrease. At high temperature, the lambda max, that is maximum wavelength, is seen at shorter wavelength, and at low temperature the maximum wavelength shifts towards longer wavelength. As in picture, at 2000 Kelvin the lambda max is between wavelength 1 and 2 micrometer, and at 1250 Kelvin lambda max is near 3 micrometer. Other laws of blackbodies. There are many laws of blackbodies. So now we should know what is Wien's displacement law. According to Wien, the wavelength maximum, that is lambda max, is inversely proportional to temperature. The graph shows the relation of spectrum versus wavelength, and the change in lambda max at different temperature varies periodically. This relation is used to calculate temperature of stars using higher intensity of wavelength. Now, Stefan Boltzmann law. They studied the relationship between energy per unit volume, which is known as energy density of temperature. This expression in terms of emitters R is as given in the formula. It gives the total energy emitted at all wavelength by the body by the area under the curve. This law explains the change in intensity with temperature. Now, Wien's distribution law. It gives the relation between energy emitted by the blackbody at given temperature within wavelength lambda to lambda plus d lambda, as given in the formula. Now comes the Rayleigh's law. It shows the relationship between number of oscillation per unit volume in frequency range nu to nu plus d nu, as in the formula, and from this formula we can calculate the energy density as the second formula. It agrees with the experimental measurements for long wavelengths. It predicts why the energy diverges towards infinity and never touches x-axis. As frequency increases, the energy density gradually increases and becomes infinite when frequency becomes infinite, which is known as ultraviolet catastrophe. Now comes the most important law of blackbody, that is Planck law. Planck developed the modern theory of blackbody radiation. It gives the explanation why with the rise in temperature the lambda max shifts to shorter wavelengths. In terms of frequency, the formula is as below. And as a function of wavelength, the formula is as given. Now, motivation from blackbody radiation. So why study of blackbody is important? So firstly, to study thermal radiation theory. Secondly, to study electromagnetic radiation. To study absorption of real bodies, blackbody is used as standard. So summary. So what we have studied till now. Blackbody absorbs all radiation and reflects nothing, so it appears perfectly black. As stars radiate like blackbody, so we can use the concept of blackbody to study about stars. At a particular temperature, the blackbody would emit the maximum amount of energy possible for that temperature. Radiation doesn't depend on the material of the subject. The only factor on which blackbody radiation depends is temperature. So that's all for today.